For number 1 on the additional problems, it says that using the reaction as it's written up there, determine the equilibrium constant, which is K, if the following equilibrium concentrations are found. All of the components are gases. So this is important because it says that all the components are gases, because only the gases provide something for the equilibrium constant. This is because gases have something special that liquids and solids don't have. Gases are able to change the number of moles, or concentration, without changing the volume. On the other hand, solids and liquids, when they change the concentration, whether going up or down, have a change in the volume. So the only ones that we worry about when we do equilibrium expressions are gases. So if one of these components was a solid or a liquid, we would just ignore it completely when we write the K equilibrium expression. Now the other thing that we have here, immediately when we see a reaction, we should think about the initial amounts, the change in the amounts, and the equilibrium amounts. So in this problem, they actually gave us the concentrations found at equilibrium. However, if they were to give us the initial amounts and the equilibrium amount of one of them, we should be able to use this chart to find the change from 0, which is for the products, to the equilibrium amount they would give us. And we should be able to connect the change that we found here based off the coefficients, just like we did last week, the ratio of 1 to 2 here, 2 to 2 here, and 1 to 2 here, of whatever this change is. And based off of that change, we should be able to either add in the products or subtract in the reactants. But in our situation, they didn't give us any of this. They actually gave us the equilibrium amounts for A, B, and A, B, C, and D. And they're just asking us to figure out the K equilibrium. What we have here are the equilibrium concentrations, and that's important because this is the concentrations that we're going to use, not the moles, but the concentration of A, B, C, and D. For C and D, I just wrote out the number as it is on the problem in scientific notation, so it's easier to write. So the first thing we have to do is figure out what the K equilibrium equation is for this reaction. Now the pattern for the K equilibrium equation is that it's always the products over the reactants. The concentrations of the products over the concentrations of the reactants, and you put the coefficients, in this case 1, 2, and 1 and 2, as the exponents for those concentrations. So for this K equilibrium equation, it would be the concentration of C to the power of 1 times the concentration of D to the power of 2 divided by A to the power of 1 and B to the power of 2. And the products are always the ones on the right side of the equation. So the products are C and D, and they would be on the top. Then all we're doing is plugging in the numbers for each of those into its particular box. At this point, all it ends up becoming is an algebra problem, because you have 4 different factors, all of which have a number that are being plugged in. Make sure to square the number for D and square the number for B. And in this case, when you work out the problem, the K equilibrium should be equal to 1.98 times 10 to the power of negative 7. So it is a super small number. For number 2, it gives us the reaction, and it says determine the equilibrium constant when you have those concentrations at equilibrium. And all of those components are gases. So, since we know everything at equilibrium, we didn't have to do anything in the chart necessarily. All we're finding is the K equilibrium. And in this case, once again, the products are those on the right. So we have, as written out, the concentration of C to the power of 2, the concentration of D to the power of 2, divided by the concentration of A to the power of 2. And then, once again, it becomes simply plugging in those numbers. Make sure to square it when it tells you to square, and make sure that you're multiplying C and D, because that's what that expression actually is. Once you do all of that, you should get an answer as 2.446 times 10 to the power of negative 12. So for number 3, they give us another equation, and they say find the equilibrium constant for this reaction based off the concentrations that you have. And you should notice something right away, that we don't have a concentration for the solid. So you have to remember that solids and liquids do not have equilibrium concentrations because they cannot change the concentration while keeping the volume constant, the way a gas can. So everything we work with for right now in the equilibrium expressions are gases. So when we see a solid, we can almost imagine that it doesn't exist. So when we write the K equilibrium expression, we have the products, which are on the right side. So we have the concentration of C times the concentration of D divided by the concentration of A with the coefficient raised to the second power. No B there. So now we know the concentration of A, we know the concentration of C and D, so all it ends up becoming is plugging in the numbers. And what you should get for the answer for K equilibrium is 3.97 times 10 to the power of negative 5. So for number 7, you have a reaction, and it tells you that the equilibrium constant is an actual number, and they give you that number. They're also giving you the equilibrium concentrations of NO and of oxygen, and they're asking you to figure out what this is equal to. So even though they give you the K equilibrium, the actual number, which is equal to 1.671 times 10 to the power of 4, we're still going to write out a K equilibrium equation with the same idea of products divided by reactants. So K equilibrium is equal to, it's equal to the concentration of NO2, which is the product, squared, because that's the coefficient, divided by the concentration of NO squared times the concentration of O2 to the power of 1. So in this case, we have the K equilibrium given, and we're trying to find the NO2. So we're using this number, plugging it in to that. We're using this number and plugging it in to that. And we're using this number and plugging it in there. Make sure to square the number for NO, and make sure that when you get everything on the denominator side in number form, what you're going to do is multiply that number to get rid of it on the numerator side. But whatever you do to one side, you're going to have to do also to the other side. And you're going to have a number equal to NO2 squared. So right now you're not done, however, because NO2 is squared and it's giving you a number. What you want is NO2 by itself. So you would have to do the square root of that to cancel out the NO2 squared and just have the concentration. And whatever you do to one side, you do to the other side. And then you should get the answer as being 0.7304 molarity. And that is that number right there. For letter B, all it's asking is the same exact thing. The only difference being that the K equilibrium, instead of being 1.67 times 10 to the power of 4, this number here is actually equal to 1.315 times 10 to the power of negative 2. And we're still finding the concentration of NO2. And what we should find for the concentration of NO2 is 6.479 times 10 to the power of negative 4. And what you notice here is that the K equilibrium on the one time for A, it was a really big number. 1.671 times 10 to the power of 4 is the same thing as saying 1,671. In B, saying 1.315 times 10 to the power of negative 2 is essentially 0.01315. And what we should know here is that when K equilibrium is greater than 1, as it is in A, that the reaction is favored to the product side. So that means that this reaction prefers to go to the right, and it favors NO2, or the production of NO2. In B, when the K equilibrium is less than 1, what that means is that the reactant side is favored above the product side. And it makes sense from the fraction level, because if this thing right here, K equilibrium, is equal to the concentration of the products over the concentration of the reactants, well, if you have a bigger number, bigger than a fraction for K equilibrium, that means that NO2, the concentration, has to be bigger because it's in the numerator. But if you have a K equilibrium that's a fraction, meaning somewhere between 0 and 1, that means the denominator, NO squared times O2, has to be the bigger number.